Hello, this is Professor Larai in section 6.5, Paired Difference in Means. Today we will go over the definition of paired data, confidence interval for difference in means based on paired data, and hypothesis test for difference in means based on paired data. Generally, experiments often consist of comparing two or more sets of data. This data is described as unpaired or independent when the sets of data arise from separate individuals. On the other hand, the data is called paired when it arises from the same individual at different points in time. Let's see some examples to understand those definitions. Previously, when we performed experiments on unpaired data, we split our sample into two groups, and we assigned treatment 1 to group 1 and treatment 2 to group 2. Then we compared the means and we found the difference. In this section, we will look at our sample as one. Each case in our sample will go through two treatments at random order, and then we will compare the values. If we follow that process, we would be performing a paired data experiment. Another example of paired data experiments are identical twin studies. Even though twins are two different individuals, biologically they share the same information. The last example of paired data experiments are when you match your cases with similar cases. For example, you would match your individuals in your sample to other individuals from the same educational, ethnical, or financial background. Again, if you perform the experiment that way, you would be performing a paired data experiment. For the next couple of slides, I will show you a couple of scenarios, and in each time you need to tell me if this is a paired data experiment or not. To study the effect of sitting with a laptop computer on one's lab temperature, 29 persons have their body temperature tested before and after sitting with a laptop for an hour. In this experiment, each case went through both treatments, so this would be considered a paired data experiment. Let's see another one. A study investigating the effect of exercise on brain activity recruits sets of identical twins in middle age, in which one twin is randomly assigned to engage in regular exercise and the other doesn't exercise. So again, any study that has to deal with identical twins is considered a paired data experiment. Let's see another one. In a study to determine whether the color red increases how attractive men find women, one group of men rate the attractiveness of a woman after seeing her picture on a red background, and another group of men rate the same woman after seeing her picture on a white background. In this experiment, our cases went through different set of treatments. Group 1 went through one treatment and group 2 went through another treatment. So this would be separate samples. Let's see one last one. To measure the effectiveness of new teaching method for math in elementary school, each student in a class getting the new instructional method is matched with a student in a separate class on IQ, family income, math ability, and reading ability. And at the end of the year, math ability levels are measured. So in this case, even though we're not doing our studies on identical twins, we are matching our cases to similar cases based on IQ, family income, math, and reading ability level. So in this case, this would be considered a paired data experiment. Now that we have defined what paired data is and we've seen a couple of examples, we will go through the process of this experiment. So as I said, each case will produce two measurements. So the first thing that you need to do is to take the differences between responses for each pair. Then you would find the mean and the standard deviation for those differences. Keep in mind using matched pairs decreases the standard deviation of the response, which decreases the standard error. And smaller standard error decreases the chances of type 2 error and decreases the margin of error. So whenever you have a chance to perform paired data experiment, go for it. To analyze the differences, we use the same formulas we learned for a single mean with some minor changes. So this formula is for the standard error. This formula is for the confidence interval, so it is statistic plus or minus t star times standard error. And the last formula over here is for the t-test, which we use whenever we perform hypothesis tests. Now the new notations are the x bar d, the SD, and ND. The x bar d is the sample mean of differences. As I said, each case will produce two measurements, and you are taking the differences of all these cases. So once you're done finding the differences, you'll find the mean of those differences. The mean of those differences is the x bar d, and the standard deviation of those differences is the SD. ND is just the number of the pairs. And since we are only studying the paired data based on differences in means, we will be performing a t-distribution rather than the normal distribution. So we will keep the same criteria, meaning our sample or the number of pairs needs to be larger than 30. And we will use the degree of freedom as ND minus 1. So let's see an example. Example 1. Do you think your pulse rate is higher when you are taking a quiz than when you are sitting in a lecture? The table below shows pulse rate collected from 10 students in a class lecture and then from the same students during a quiz. Notice how each case is producing two measurements. The question is, construct a 99% confidence interval for the difference in mean pulse rate between students taking a quiz and sitting in a class lecture. If this was a separate sample experiment, then some students would measure their pulse rate during the lecture, and then another group of students would measure their pulse rate during a quiz. However, in this experiment, each student measured their pulse rate twice, once during a lecture and another during a quiz. So you have two measurements for each student. Thus, we are using paired data formula. So our first step would be taking the differences of those measurements. So look at case number 1. Take the difference, 75 minus 73 is positive 2. For case 2, 52 minus 53 is negative 1. For case 3, 52 minus 47 is positive 5, and so on. So once you find all these differences, you will take the mean, and that will be 2.7, and you will find the standard deviation as well, and that will be 9.93. So I can go ahead and start the t-distribution. My only concern is that my sample has 10 students, which is less than 30. So I need to make sure that my sample is symmetric without any outliers, otherwise I cannot use the t-distribution. So I start a dot plot for this sample, and this dot plot will look like this. This is for a positive 2, for the negative 1, positive 5, negative 8. So I'm taking the values from here because this is now my sample. And I keep doing this for all 10 measurements. Once I'm done, I look at the mean. This will be around here, 2.7, and you can see that I almost have the same number of dots left and right, meaning that my sample is symmetric without any outliers, so I can go ahead and perform the t-distribution. So I know that the mean difference is x bar d equals 2.7, and I know that the standard deviation is 9.93. I'm only missing the t-star. So the t-star is found using StatKey, and for that you need to know that we have a degree of freedom of 10 minus 1, which is 9, and we are constructing the 99% confidence interval. So let's do this through StatKey. So we enter the degree of freedom of 9, and this is a confidence interval, meaning I'm going to always choose the two-tail and change this percentage to the 99. Doing so will show me the t-star down there, so I can say that the t-star is about 3.25. So now that I have the t-star, the x bar d, and the SD, and I know that there were 10 students in my experiments, I have all the variables in my equation, so I'm going to go ahead and perform that. This is the statistic plus or minus t stars times SE, and I have all the numbers. You plug it in and you'll find that the interval will be between -7.5 and 12.9. The way we read this interval, we say based on these results, we are 99% sure that the mean pulse rate for students during a quiz is between 7.5 beats less and 12.9 beats more than the mean pulse rate during a lecture. Now, since I have values that are between negative and positive, then what I can interpret out of this is that each student is different. Some students will have more or higher pulse rate during a quiz, some will not. Let's see an example that deals with hypothesis testing. So in example 2, researchers designed a study to determine if skin wrinkled from submersion in water performed better at handling wet objects. They gathered 20 participants and had each move a set of wet objects before and after submerging their hands in water for 30 minutes. The response is the time it took to move the specific set of objects with wrinkled hands minus the time with unwrinkled hands. The mean difference for moving wet objects was -15.1 seconds, with a standard deviation of 13.4 seconds. Assuming the sample is from symmetric population, test to see if the wrinkled hands were significantly faster than unwrinkled hands at moving wet objects. Now, since we are trying to prove something, I need to perform the hypothesis tests format. Since the response time is the time it took, and I'm doing this in terms of wrinkled minus unwrinkled, so I'm expecting negative values, because if you have faster time, then you have a smaller value. So as if you're doing smaller value minus larger value, so you'll have a negative value at the end. So let's do this. So first, let's state the hypothesis. You have the null hypothesis, mu d equals 0, meaning that the average difference in time is 0, or as if you're saying that there isn't any really difference in time between the two groups. The alternative is saying that the average difference in time would be negative, and this is what we are trying to prove. We are trying to prove that moving objects with wrinkled hands is faster. The next, we need to find the t-test, and for that we need the formula. So t equals statistic minus null over standard error. And the statistic is given to me in the problem. That's -15.1 minus 0 is the null over the standard deviation is also given to me in the problem, divided by the square root of n. And since I had 20 participants, so n equals 20, plug this in your calculator and you'll get t equals -5.04. The third step is to find the p-value, and for that I need the degree of freedom, which I can get from 20 minus 1, so I know the degree of freedom is 19. I need to know which direction I should follow, and this is always from the alternative hypothesis, so this is a left tail test, and I need the cutoff for t, and that's -5.04. So let's do this. So you go to t distribution, enter the degree of freedom, left tail test, and adjust the t to -5.04. And you'll have the p-value as 0.00004. So now that you have the p-value, you'll compare it to alpha, and obviously p-value is less than alpha, so we reject the null. And we say that we do have very strong evidence that wrinkled hands are significantly faster at moving wet objects, possibly indicating that hands adapt to being submerged in water. And that's it for 6.5 or Math 117 in that matter. Please do the homework and let me know if you're having any difficulties. Thank you.